Today we'll be covering section 12.4 on the addition and complement rules. Before we begin, I want to say that most of the problems in this section can be solved using techniques we already know. But occasionally we'll come across certain problems when we need to learn a little bit more about probability, and occasionally we'll find out that it's convenient to use some more formulas and have them in our toolbox. So I'm going to do something that I don't usually do. I'm going to go ahead and give you a listing of the formulas that we're going to add to our toolbox in advance of when we've actually talked about them. I think it'd be good to let you look at what we're going to be using, mainly for the reason that I said earlier, we don't always even need them, but they will be here if we do need them. The first is called the addition or union rule for probabilities. It simply says that the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. And remember, or means union and means intersection. The complement rule. If E is an event and E with a superscript C is the complement of the event, then the probability of E complement is equal to 1 minus the probability of E. The product rule for independent and dependent events. If two events E and F are independent, then the probability of E and F is simply the probability of E times the probability of F. Now the dependent version of this rule uses some notation we haven't even introduced yet, but I'm going to go ahead and do it anyway. We'll come back to it later and talk more about what the new notation means. But it says, if two events E and F are dependent, then the probability of E and F is equal to the probability of E times the probability of F given E, which is also equal to the probability of F times the probability of E given F. Remember, I haven't even introduced that notation where the vertical line is used here in this context yet, but I will. That leads to something called conditional probability, and I've got two formulas related to that. One says the probability of E given F is equal to the probability of E and F divided by the probability of F. Remember, when I say E and F, and means intersection. Also, the probability of F given E is the probability of E and F divided by the probability of E. Before I leave this, I told you I'm going to rotate back to this later, but I will say, if you use that notation with the vertical line, it's read the probability of E given F. The vertical line is read as given, or given that. So of course the probability of F given E when the E and the F are flipped around the vertical line. Like I said, we'll come back to this later, but this is the addition to our toolbox of formulas. Sometimes we'll need them, sometimes we'll just be able to go back and do these problems using the things we already had, but they're there if you need them. Suppose we want to calculate the probability of rolling two dice and getting a sum of either 5 or 9. And you notice I call this getting a sum of 5 an event called E sub 1, and the sum of getting a 9 an event called E sub 2. That's just for convenience. We're trying to roll two dice and find the probability of getting a sum of either 5 or 9. You really don't need any of the new formulas to do this. This is just like a problem we might have been able to work earlier, and I want to emphasize that what you really need to do is build your 2x2 table for rolling two dice, which gives you the sample space, and then look, we're looking for a sum of 5. That's the event I called E sub 1. There are 4 possibilities. You roll 4, 1, 3, 2, 2, 3, or 1, 4, or a sum of 9. That's the event I called E sub 2. There happen to be exactly 4 possibilities for that as well, either a 6, 3, a 5, 4, a 4, 5, or a 3, 6. So the probability the sum is either 5 or 9 is simply how many ways you can get a 5 or a 9, which happens to be 8, over the number of ways you could get any sum, which as we know from earlier problems is 36. WebAssign will accept 836 as the answer, or you can reduce it to 2 9s. But there is something about those last two examples worth noting. There's a difference. Look at those two. I'm flashing on the left, the first one I did, on the right, the second one I did. Going back to the one on the left, the probability the sum was 5 or 7 turned out just to be the sum of the probability that the sum was 5 and the probability that the sum was 7. In other words, there were 4 events that gave me a sum of 5. So the probability of getting a sum of 5 is 436, but there are also 4 that gave me a sum of 8. So the probability of getting a sum of 8 is also 436, and 436 plus 436 is 836. But if you look on the right side, the probability that a number is greater than 2 or odd turned out to not be equal to the probability that the sum was 2 plus the probability that the sum was odd. If you look at it, the probability that the sum was 2, 3, 4, 5, 6, 7, 8, 9, 10 was 8 out of 10. The probability that the sum was odd was 5 out of 10. Well, obviously, 8 tenths plus 5 tenths is 13 tenths, not 9 tenths. So on the left, I was just able to take the two events separately and add up the probabilities and get the correct answer. On the right, if I tried that trick, it wouldn't work. Why is that? It's an important distinction. Think about it just a minute. In a nutshell, it's because on the right, some of the values are greater than 2 and odd. Remember that when we did this problem on the right, there were certain numbers that were both greater than 2 and odd. For example, 3 is greater than 2 and odd, 5 is greater than 2 and odd, 7 is greater than 2 and odd, and 9 is greater than 2 and odd. So there's an overlap between those counts. On the left, that didn't happen. When you looked at the numbers that summed to 5 and the numbers that summed to 7, there was no overlap. That's what caused the difference. Noting this leads to an important result called the addition or union rule for probabilities. Remember, that's one of the ones that I flashed up earlier. It says that the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. And if you look at that formula, it encapsulates the difference that we just noticed between those two earlier examples. You could have used this rule to solve both of the earlier problems, but you don't have to. We were able to figure out a way to do it without using the formula. But I will say that if you did use the formula for the first one, where the events were mutually exclusive, the sum being 5, there was no overlap with the sum being 7, there was nothing to subtract away. If you take that minus part of the formula, it would have been 0. The probability would be 0 that a sum could be 5 and 7. However, on the second one, there was an overlap. There were numbers bigger than 2 that were also odd. This formula takes care of that. Think about that, what that means. If the events are mutually exclusive, the probability of them both occurring together is 0, so you're actually subtracting nothing. So the formula also allows for the possibility that overlap is not probability 0. So the formula works either way, but if they're mutually exclusive, remember there's just nothing to subtract. The formula just degenerates to having to subtract nothing. Now let's look at some problems where we might want to think about it in terms of using this formula. If we select a single card from a standard 52 card deck, what is the probability that we draw either a heart or a face card? So the probability of a heart or a face card. Recall what this standard 52 card deck looks like. It has 4 suits, 12 face cards, etc., etc. So the probability of a heart or a face card is just going to be the number of hearts or face cards over the number of cards in the deck. Well, if you look at the hearts or face cards and just count them, the face cards are the cards that actually have faces on them, and you've got the hearts as the other possibility. If you just count, you'll see that there are 22 of them over the number of cards in the deck, which is 52. So you get 22 over 52, and if you want to reduce it, you get 11 over 26. Suppose I wanted to actually use that addition rule rather than just figure it out as I just did here. It would still work. I would just simply take the probability of getting a heart. Well, remember, there are 13 hearts in the deck. So the probability of getting a heart is 13 over 52. Then I would calculate the probability of getting a face card. Well, there are 12 face cards in the deck, 4 jacks, 4 queens, 4 kings. So the probability of getting a face card is 12 over 52. And if I apply the formula, I'll see that I still need to calculate the probability that a card is both a heart and a face card. And if you look at the picture, there are 3 hearts that are also face cards. That's the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So the probability that the card is both is 3/52. And if you plug into the addition rule formula, you'll notice that you get the probability of getting a heart is 13/52, plus the probability of getting a face card is 12/52, minus the probability that you get a card that's a face card and a heart. That's 3/52, and that's 13 plus 12 minus 3 is 22. So you get 22 over 52, which is 11/26, which is exactly the answer we got earlier by doing it without using the addition rule. So this is just another example of where the addition rule works, but you could really do it without it. Here's an example where using the rule is really the best way to do it, the most straightforward way to do it. It says if the probability of A is 0.3, the probability of B is 0.4, and the probability of A and B is 0.2, find the probability of A or B. Remember, and is intersection, or is union. So I would say the most straightforward way to do this particular problem is to use the formula. If you write the formula down replacing E and F with A and B, you get the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Well, we know the probability of A is 0.3, we know the probability of B is 0.4, and we also know that the probability of A and B is 0.2. So a little bit of arithmetic tells you that the final answer, the probability of A or B, is 0.5. That's the most straightforward way to do it. Another example where the formula is the most straightforward way to do it. What if the probability of A is 0.3, the probability of B is 0.4, the probability of A or B is 0.5, but this time we're looking for the probability of A and B. So it's the same formula, but you know different things. Here you know the probability of A or B is 0.5, the probability of A is 0.3, the probability of B is 0.4, and you're looking for the probability of A and B. It becomes a small algebra problem, but it's easy enough. 0.3 plus 0.4 is 0.7. If you move the negative probability to the left and move the 0.5 to the other side, making it negative, you'll end up finding that the probability of A and B is 0.7 minus 0.5, which is 0.2. These are both examples where using the addition or union rule for probabilities is the most straightforward way to solve the problem. Use the following table to find the probability that a randomly chosen member of the Student Government Board is a freshman or lives in off-campus housing. They give you a table. This is another problem where you probably can just do it by the old techniques. You want to know the probability that a person is a freshman or lives off campus. So you look at your chart. There are 5 freshmen and there are 5 students who live off campus. So we want to know the probability of being a freshman or living off campus. You can't just say 5 plus 5 because there's one person who overlaps. There's one person who is a freshman but also lives off campus. So when you count the number of freshmen or students living off campus, you have to say 4 plus 1 plus 4. That's only 9. And then when you count everybody, you get 4 plus 1 plus 2 plus 0 plus 4 plus 2 plus 1 plus 0 plus 4 plus 0, 0, you get 17. So the answer is 9/17. Again, you could use the addition rule to get the answer, but I would recommend just doing it straightforwardly. Consider the experiment of rolling 2 dice. Let A be the event of rolling a sum of 8, and let B be the event of rolling a double. A double means you get the same number on both dice, like a 2 and a 2 or 5 and a 5. Find the probability of getting either a sum of 8 or a double. Again, when you're rolling 2 dice, you think of that as a 2-stage experiment, so you build a table. We've talked about that before. The probability of getting an 8 sum or a double is going to be the number of ways of getting a sum of 8 or a double divided by the number of ways to get any sum. So if you look at the numerator, let's first look at the number of ways of getting a sum of 8. You could get a 6-2, a 5-3, a 4-4, a 3-5, or a 2-6. Then look at the number of ways to get a double. You could get a 1-1, a 2-2, a 3-3, a 4-4, a 5-5, or a 6-6. If you want to count all those possibilities, notice there's an overlap of 4-4. So when you're counting, you don't want to count that 4-4 twice. If you count them, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't count that 4-4 twice. So that gives you 10 over the number of ways to get any sum. Well, it's, as we've learned from doing these type problems multiple times, there are 36 possibilities. So the answer is 10 over 36, and if you want to reduce it, you get 5/18. Again, we didn't have to explicitly use the addition rule for probabilities, although you could. Let's go to the complement rule that we introduced in our toolbox at the beginning. The complement of an event. Let's take an experiment where we're rolling a single ordinary dice. The sample space obviously is going to be either 1, 2, 3, 4, 5, or 6. So if we want to look for the event that we rolled a 3, the probability of doing that is the number of ways you can get a 3, which if you're rolling a single die, there's only one way to do that, over the number of elements in the sample space. So the probability of rolling a 3 is 1/6. The complement of that event, and we're going to use the notation E with the superscript C. Some texts use E with an accent symbol like we used back when we talked about regular set operations, but if you see it either way, it means the same thing. E with a superscript of C or E with an accent symbol. It's sort of, in a sense, the opposite of the event. So if you're looking for an outcome, the complement is everything except that outcome. So if we're talking about the problem we did above, if the event E was getting a 3, then E complement is not getting a 3. So in this case, if we wanted to write out E complement, it would be everything except 3. So it would be 1, 2, 4, 5, or 6. So when we're talking about the complement of event, that's what we mean. Everything but what makes up the event. There are 5 things that aren't 3s out of possible 6, so you get 5, 6. And notice that the probability of getting a 3 is 1/6, and the probability of not getting a 3 is 5/6. And that's not a coincidence. That's what the complement rule says. It simply says if you know the probability of an event and you want to know the probability of the complement of the event, you just say 1 minus the probability of E. And the importance of that rule is, it seems sort of obvious, but it's very useful because some problems it's really easy to calculate the probability of an event, and it's a little more difficult, or more than a little more difficult sometimes, to calculate directly the probability of the complement. But if you can calculate the probability of the event, all you have to do is say 1 minus that probability, and you'll automatically have the probability of the complement of the event. So this is important. It's a very handy tool to have in your toolbox. For example, if I ask you to find the probability of not rolling a sum of 11 when you're rolling 2 dice, again, you'd build your table. The probability of not rolling an 11 is the same thing as 1 minus the probability of rolling an 11. The probability of the complement of something is 1 minus the probability of that something. So it's very easy to calculate the probability the sum is 11 because there are only 2 possibilities. You can get 6, 5 or 5, 6. So the probability of getting a sum of 11 is simply 2 out of 36. So the probability of not getting a sum of 11 is 1 minus 2 out of 36, which would be 34 out of 36. Complement rule is a very powerful tool in your toolbox. If you want to reduce that to 17/18, you're free to. I want to talk about a little bit about the English language as relates to this. It turns out that when we're doing probabilities, we tend to come to these problems where we're asked to find the probability of at least one something. And I want to talk a little bit about that in particular so that when you see it, it won't be confusing. For example, if I roll a standard die 3 times, What's the probability we get at least 1 4? You see that at least 1 quite often. At least 1 4. Well, think about it. At least 1 4 means you get exactly 1 4, or exactly 2 4s, or exactly 3 4s. That's what it means to have rolled at least 1 4 in the context of rolling the die 3 times. One way to answer this question is just to do 3 separate probability calculations and just add up the results. Just find out the probability of getting exactly 1 4, then find the probability of getting exactly 2 4s, then find the probability of getting exactly 3 4s, and just add them all up. That's one way to do it. You could take this, and this, and this, and just add up the 3 separate probabilities. That's quite a bit of work. There's a better way. The better way is to use the complement rule. Because if we roll the die 3 times, there are only 4 possibilities altogether. We've talked about 3 of them. We've talked about getting 1 4, or 2 4s, or 3 4s. There's only one other way, and that's to get no 4s at all. So wouldn't it be much easier to calculate the probability of not getting any 4s, and then say 1 minus that? And that's what I'm going to do. The complement rule says the probability of getting at least 1 4 is 1 minus the probability of getting no 4s, because getting no 4s is the complementary event of getting at least 1 4. And getting no 4s is a much easier probability calculation. So how do we calculate the probability of getting no 4s? And this comes back to the stuff we talked about earlier. Remember when we started studying this, I asked you if you know how to count. The solution of that problem requires us to count using some of our combinatoric formulas, and that's why we studied them, so we could use them. So if a standard die is rolled 3 times, what is the probability we get at least 1 4? Well, we just talked about that the easiest way to do it is to calculate the probability of getting at least 1 4 as 1 minus the probability we don't get any 4s. That probability of getting no 4s is the key calculation in the whole problem once you understand what you're trying to do. So how do you calculate the probability you don't get any 4s? Well, I would think of it this way. The probability of getting no 4s is the number of ways to get anything but a 4 divided by the number of ways to get anything with your 3 rows. I think I'll start with the denominator first. Let's find the number of ways to get any 3 rows. Going all the way back to the counting principle, if you're looking for the number of ways to get any 3 rows, remember each row can be a 1, 2, 3, 4, 5, or 6. So think of this as a 3-stage experiment. You can look at how many ways you can get something for row 1, row 2, row 3. The counting principle says to multiply them together. So the number of possibilities for the first row, well, there are 6 possibilities. As for the second, there are still 6 possibilities, and for the third, there are still 6 possibilities. So the counting principle says the possible die rolls you can get when you roll 3 times is simply 6 times 6 times 6, which happens to be 216. That's the denominator. But what about the number of ways to get anything but a 4? Well, after having done the calculation we just did, I think you'll see that it's pretty easy to look at the numerator and see that it's the same thought process, but this time we're not allowing the possibility of getting a 4 because we're looking for the number of ways to get anything but a 4. So we knock the 4 out as being a possibility, but the process stays the same. We're still doing 3 die rolls. We just don't want any 4s. So there's only 5 possibilities for the first die roll if you don't want it to be a 4. There are only 5 possibilities for the die roll 2 if you don't want it to be a 4, and there are only 5 possibilities for die roll 3 if you don't want it to be a 4. 5 times 5 times 5 is 125, so the probability of getting no 4s is simply 125 over 216. But that wasn't the final answer. We want to know the probability to get at least 1 4. The key calculation was getting the probability of no 4s, but it wasn't the final answer. The probability is 1 minus that, which would be 91 over 216. How about this? If you draw 3 cards from a standard deck without replacement, what is the probability that at least one is a face card? Write your answer as a percent rounded to 1 decimal place. So as we learned, the probability of at least one something is 1 minus the probability of none of that thing. So in particular, the probability of at least one face card is 1 minus the probability of no face cards, or 0 face cards. And as we've seen before, that probability of 0 face cards is the key calculation. Well, what is the probability of no face cards? There are 12 face cards in the deck. We've done this multiple times, so that means there are 40 cards that aren't face cards because 52 minus 12 is 40. So we think of partitioning the deck into face cards and non-face cards. There are 12 face cards, there are 40 non-face cards. So the probability you don't get a face card is the number of ways not to get a face card. In other words, the number of ways to get anything but a face card divided by the number of ways to get any 3 cards. We've done these problems in earlier sections. When we're drawing face cards, we don't care about order, because when you pull a card out of the deck and put it in your hand, it doesn't matter what order the card came into your hand. So this is a combination. If we're trying not to get a face card, we've got to draw from the 40 things that aren't face cards. So it's a combination of 40 things, and we're choosing 3 cards, so it's a combination of 40 things taken 3 at a time. Down bottom, when we don't care what the cards are, it can be any of the 52, but we're still drawing 3 cards. So it's a combination of 40 things taken 3 at a time, that's the number of ways to get anything but a face card, over a combination of 52 things taken 3 at a time. That's when you don't care what the cards are. You're drawing 3, but you don't care what they are. And in case you really have forgotten your shift combinations to get your calculator answer, I put them there for you. I hope you didn't need it. They ask you to do a decimal approximation, so you need to change that now to a decimal. That's 0.44706. They ask you to change it to a percent rounded to 1 decimal place. So take plenty of decimals because you have to change it to a percent and then round it. So do not just write 0.44, write several decimal places. So it's 0.44706 to several decimal places. So you continue your calculation. The probability of getting at least 1 face card is 1 minus the probability of no face cards, which we've calculated to be 0.44706. Notice I'm emphasizing yet again, carry plenty of decimal places during this calculation. Round off in the very last step. To do that subtraction, you get 0.55294. You're still not ready to round because it says to give your answer as a percent rounded to 1 decimal place. So you first change it to percent and then you round. You sort of see now why I'm emphasizing how important it is to carry plenty of decimal places. Now change it to percent, which means you move the decimal place 2 places to the right, and finally you round that to 1 decimal place. Suppose we take the problem that we just solved and change it ever so slightly so that now we're drawing 3 cards from a standard deck, but we're drawing with replacement. We still want to know what is the probability that at least 1 is a face card, and we'll take our answer as a percent rounded to 1 decimal place. So the only difference here is that we're drawing with replacement. How does that change everything? What's different about it? Because we're drawing with replacement, this does not involve counting things using either the permutation or combination formulas. Those are what we use when we have distinct objects and we're looking at how many arrangements or how many ways we can choose from those. When we're drawing with replacement, it just doesn't fit that. So we have to go back to the counting principle for problems like this. And that's the difference between this problem and the one you just solved. But still, with the complement rule applies, and we can calculate the probability that there's at least 1 face card by calculating 1 minus the probability that there aren't any face cards or that there are 0 face cards. So this part doesn't change at all. And that calculation of getting 0 face cards is really the key to the whole thing, because once we get that, the final answer will be just 1 minus that answer. Remember also that there are 12 face cards, so if we're trying to not draw a face card, we're looking for one of the non-face cards, and there are 40 of them because 52 minus 12 is 40. And as before, the number of ways you can get no face cards is simply the number of ways that you don't get a face card when you're drawing those 3 cards over any possible way you could draw 3 cards from the deck. And again, this time with replacement. So the answer for the 0 face cards probability will be a fraction, and we have to calculate the numerator and denominator, and we're home free. But as I said, we're doing it with replacement. We can't calculate with our combination formulas. We have to go back to the counting principle. And here it says we're just doing 3 events, 3 subtasks, however you want to think of it. And we've got to count the number of ways you can do each one. Well, if you're trying to not draw a face card, on the first draw, there are 40 ways of not getting a face card. And since you're putting the card back in the deck, there are 40 ways to not choose a face card on the second draw. And again, because you're putting the card back, there are 40 ways not to choose a face card the third time. So the numerator will be 40 times 40 times 40. How about the denominator? Well, same thought process, but in the denominator, you don't care what it comes out to be. It could be any of the 52 cards. And again, because you're putting it back in, you still have 52 cards to choose from. You don't care what the card is. And the third draw is the same. You have all 52 cards to choose from, and you don't care what the card is. So the result will be 40 times 40 times 40 over 52 times 52 times 52. That's 64,000 over 140,608. Now the answer they want is decimals rounded to one place and as a percent. So we need to change that fraction to a decimal at some point. You might as well do it now. Always take quite a few more decimal places than you think you're going to need. It says to round it to one decimal place, but it also says to write as a percent. Writing it as a percent causes you to move the decimal place 2 places to the right. Then you want another decimal place of accuracy, that's 3. So definitely take, I would say, 5 or 6 decimal places for sure. So I wrote it as 0.455166. Now remember, the probability of at least one face card is 1 minus the probability of no face cards, and we just calculated the probability of no face cards, so 1 minus that value is 0.544834. Now we're done except for the fact they asked us to do it as a percent rounded to one decimal place. So changing it to a percent moves the decimal place 2 places to the right. And then you can see that that first decimal place is a 4, but the hundredths place is an 8, so that 4 rounds up to a 5. So as a percent rounded to one decimal place, it would be 54.5%. So if you draw 3 cards from a standard deck with replacement, the probability that at least one is a face card is over 50%, 54.5% approximately. Now in the next section, we'll learn another method of solving this type of problem that you might find a little easier, but for now, this will get you there. Now how about a problem like this? I'm trying to give you variations of problems that on the surface sound very similar, but may have a different technique of solving them because other techniques that you've been using don't apply. How about this? A pair of dice is rolled 3 times. What is the probability we get a sum of 6 at least once? And this time, they're not asking for a percent answer, but they do want the final decimal rounded to 3 decimal places. We worked a problem similar to this before, except that we didn't roll a pair of dice, we just rolled 1 die. But I do want to go back and remind you of all those similarities. Not only is it similar to that one, but it's also very similar to the one we just worked with cards. The difference there is that we're doing probabilities based on 2 dice here instead of drawing cards from a deck. And as I said, it's extremely similar to one we did somewhat earlier in this lecture where we were rolling just a single die, but otherwise very similar. So I put up in the corner a screen capture from that calculation, and you can see what we did, and we just did it a few minutes ago, so it should be fresh on your mind. The point being, neither of the problems involving die rolls, either this one with 2 dice or the other one involving 1 die, which are independent events, rolling a pair of dice once and rolling them again, those events are completely independent of each other. The probabilities don't change because of a previous roll. Nor the previous card problem where we drew with replacement. Because we were drawing with replacement, that made those draws independent. None of the problems involve counting things with either permutation or combination formulas. We can't use those when we're drawing with replacement or any case where they're independent events. So again, we've got to go back to the counting principle for this solution. But otherwise, It's very similar to the one die roll problem. If you look at that in the lower right corner, the only difference is instead of looking at probabilities involving getting 4s, which is what the other problem resolved, we're trying not to get a sum of 6. Now, anytime you say the sum of rolling 2 dice, you've got to remember that we've got to go back and look at the sample space for rolling 2 dice. There's 36 possibilities, and we've done this multiple times. But just to emphasize this, in the lower right-hand corner, we went from looking for the probability of getting any 4s when we're rolling a single die to what we really want now, which is the probability involving sums of 6. That takes us to the sample space in the upper right-hand corner, which is a 36-member or a 36-element sample space. Once we get this, all we have to do is figure out the value that goes in the numerator and denominator, and I think maybe it's easier to start with the denominator. So let's look at the denominator first. Using the counting principle, remember I said we'd have to go back to the counting principle for these problems where the events are independent. We're going to do 3 rolls of a pair of dice. On the first roll in the denominator, we don't care what the sum is. So it could be any of those 36 sums. So you got 36 possibilities for the first row, 36 possibilities for the second row, 36 possibilities for the third row, and 36 times 36 times 36 by the counting principle is 46,656. That's the denominator of our answer for the probability of getting no sums of 6. Let's move to the numerator. Now in the numerator, we don't want any sums of 6. We're looking for the probability of getting no sums of 6. Well, if you look up there, there are 31 of them. 5, 1 adds to 6, 4, 2 adds to 6, 3, 3 adds to 6, 2, 4 adds to 6, 1, 5 adds to 6. In other words, only that diagonal line of sums that I did not circle add to 6. We want the ones that don't add to 6. And if you count those circles, or just say 36 minus 5 that weren't circled, you'll see that there are 31 possibilities. And again, this is a counting principle problem, and we've got 3 rows. On the first row, any of those 31 that I circled are okay. None of those 31 give a sum of 6. Again, if you roll a second try, same thing, 31 possibilities. Third row, again, there are 31 possibilities. All you're screening for are sums that are not equal to 6. And by the counting principle, 31 times 31 times 31 is the total number. It comes out to be 29,791, and that answer goes in the numerator. So if you take your calculator, you get about 0.63852. Again, take plenty more decimals than you need because you want to make sure your rounding error doesn't cause you to miss the problem. Also remember, we're not looking for the answer, not the final answer, as being the probability that there are no sums of 6. We're actually looking for the probability that you get at least one sum of 6, but we know by the complement rule that the probability of at least one sum of 6 will be 1 minus the probability of no sums of 6. We just calculated the probability of no sums of 6 being the 0.63852. So if you plug that in and subtract 1 minus that, you get 0.36148. They ask us not to change it to a percent this time, but just to round it to 3 decimal places. That would be 0.361, rounded to 1 decimal place. So the probability of rolling a pair of dice 3 times and getting at least one sum of 6 is 0.361. In wrapping up this lecture, I do want to say one thing. When you're practicing and working through these problems and similar problems, try looking at the big picture. If you're isolating each problem as a separate thing and just concentrating on solving that problem as you move from problem to problem, you're probably not seeing the big picture, and when you come back to those kinds of problems on the test, you may have trouble solving them. Now, I'm going to mention a few things, but this is not an exhaustive list. But for one thing, I mean by that, just the stuff that we've been dealing with recently about whether you're drawing cards with replacement or without replacement. When you're rolling die, 1 die, 2 dice, you've got to be careful. If the things involve independent events like rolling dice or drawing cards with replacement, you're generally going back to the counting principle because the combination and permutation formulas are generally used to count arrangements or choosing objects from distinct objects. And that simply doesn't apply when you're drawing with replacement or rolling dice. That's the first thing. You need to notice when you're reading the problem, is it an independent event, rolling dice, drawing with replacement, or is it a dependent event? If it's a dependent event, when you're drawing cards from a deck and not putting them back, generally you'll be able to count using your combination formulas. So that's one big picture item. Another thing I'd mention in closing is that the usual strategy when you're computing the probability of at least one of something, you handle that by applying the complement rule. In other words, go ahead and calculate the probability of getting none of those things, and then the probability of at least one of them is 1 minus the probability of none of them. There are other things I could mention, but I just want to get you thinking about looking for the big picture as you work through these problems. It's going to make your test-taking experience much better. Section 12.5 on conditional probability. I want to talk about the idea of independent and dependent events. I alluded to that in the earlier formulas when I put up those formulas in advance. Independent events are ones for which the result of one event does not affect the probability of the occurrence of the other. There are some simple examples that we'll go through, but I need to throw up the thing to contrast it with, which are dependent events. Dependent events are one for which the occurrence of one event affects the probability of the occurrence of the other. Now that you can see the contrast, I want to put some examples up and see if I can make it even clearer. Let's decide whether the following events are dependent or independent. Doing your assignments and passing your math class. Do you think doing your assignments might have some effect on the probability of you passing your math class? Yeah, I think most people would agree to that. So those are dependent events. One thing can affect the probability of the other thing. How about this? Running daily and winning the New York Marathon. Again, I think most people would agree that that might have an effect. That daily running might very well have an effect on how probable it is that that person will win the New York Marathon. So I'd say, again, those are dependent events. How about this? Winning the lottery and winning a spelling bee. It's really hard to imagine how winning a lottery could affect the probability of winning a spelling bee, or the probability of winning a spelling bee would have any effect on the probability of winning a lottery. So those two events are independent. Getting heads on a coin toss and rolling a 6 on the standard die. Flip a coin, does it matter what you get in terms of it changing the probability that you're going to roll a 6 on the standard die? No, I don't think so. So those are also independent events. This sort of gives you an example of what we mean by dependent and independent. You mainly need an intuitive idea of what they mean. How about this? Drawing an ace, then drawing a 2 from a deck of cards without replacement. Now think about this. If you draw an ace out, you don't replace it, and then you draw a 2, that does affect the probability because since you didn't put that ace back in, you're only drawing from 51 cards the second time. There is a dependence there. Drawing that ace out and not putting it back in makes those two events dependent. If you put the ace back in before you drew again, then that would erase the dependence and they would be independent events. These are very important distinctions. You need basically an intuitive idea, but having an intuitive idea is extremely important. And this leads to something called the product rule for independent events. If two events, E and F, are independent, then the probability of E and F is the probability of E times the probability of F. That was one of the tools that I flashed up at the very beginning and said we would get to it later. Suppose you flip 2 coins. What is the probability that the first flip is heads and the second flip is tails? The coin flips are independent. What I get the first time I flip the coin has absolutely nothing to do with what I get the second time I flip the coin. So that means they're independent. So that tells me that the probability I get a head and then a tail is simply the probability I get a head times the probability I get a tail, because that's what the product rule for independent events says. Well, the probability I get a head is 1/2. The probability I get a tail is 1/2. So the probability I get a head followed by a tail is 1/4. A half times a half. That's the product rule for independent events. Just want to say that you could have worked this problem with a tree diagram. If you look at your first toss as being the first stage of a two-stage experiment, the probability of getting a head is 1/2. And then once you've done a head, the probability of getting another head is 1/2, but the probability of getting a tail is also 1/2. So if you look at the branch that goes from heads to tails, you see it's 1/2 probability you get a head, and there's 1/2 probability you get a tail. And we learned earlier that the probability multiplying down a branch is the and probability. So the probability of getting a head and a tail, where the first is a head and the second's a tail, it would be 1/2 times 1/2, which is 1/4. So we did learn something in earlier sections that would allow you to get that same answer with a tree diagram. But treating it as just two independent events is much simpler. Now I want to talk about conditional events. That's the subject of section 12.5. And this is also where I said earlier we introduced some new notation. The conditional probability of event E occurring given that event F has occurred is the probability of the event E occurring taking into account that event F has already occurred. And that's what the adjective conditional means. Conditional probability means the probability conditioned on the fact that something else has already occurred. It's good probably to introduce this idea through an example. Let's let E be the event that the sum is 5 when we're rolling 2 dice. What is the probability of E? Well, that's just the probability we get a sum of 5, and we know how to do that. We draw our 2x2 table, and we count the sums that come to 5, which happen to be 4, and we get, by the basic probability principle, it's the number of ways of getting what you're looking for, which in this case is a sum of 5, divided by the number of ways you can get anything in the sample space, which we know there are 36 things, so it would be 4 over 36. If you want to reduce it to 1/9, you can. But what if I tell you that I've already peaked? I've done the die roll already, and I'm holding my hand so you can't see it, but I've peaked, and I'm telling you something about it. I'm not telling you what the sum is, but I'm going to tell you, well, I'm not telling you what it is, but it's odd. Does that matter? Does that change the probabilities because I gave you some new information? And the answer is, in general, yes, that will make a difference. So what I really want now is the probability the event E happens, which is getting a sum of 5, given that additional information, given that the sum is odd. That additional information is important because if I know the sum is odd, that changes the sample space because I don't have to consider any even sums anymore. So I can get rid of every sum that comes out even. 1 plus 1 is 2, that's even. 5 plus 3 is 8, that's even. 5 plus 5 is 10, that's even. 6 plus 6 is 12, that's even. So I can get rid of all of those. So that additional information is extremely useful. I can throw out the things that no longer contend because I know it's odd. The evens don't contend anymore. So the probability of E, given that the sum is odd, is just the number of ways that E can happen with that new condition, in this case that the sum is odd, divided by how the sample space changes given that new condition. So you're still doing a count of the event E, and you're still doing a count of the event S, but you're taking into consideration that something has happened and you have more information than you had to start with. That's what I mean when I say with condition. Well, once I crossed out all the even sums, there were 36, half of the sums were even. That knocks the sample space down to 18. There are only 18 odd sums. And then I look, none of these sums adding to 5 got knocked out because they were all odd, so there's still 4 of those. So the probability of the sum being 5, if I know that the sum was odd, is going to be 4/18. It would have been 4/36 had I not known that. So instead of the probability of the sum being 5 being 1/9, now the probability that the sum is 5, with that additional knowledge, that knowledge being that the sum was odd, now has doubled to 2/9. Yes, it does matter, or at least it can matter. You can see here the probability doubled. Knowing that information, double the probability. So, to sum up, when we have a probability which includes an extra condition, and in this problem it was that the sum was odd, that probability is called a conditional probability, and we have a special notation for it. And if we go back to that previous example, the probability of E, I just wrote this sort of intuitively, the probability of E, comma, given that the sum is odd, we're going to modify that. I just wrote that out kind of intuitively. Suppose we call that condition F. In other words, the sum being odd is a new condition called F. So the sum being 5 was the event E. Now we're going to call the sum being odd the condition F. Then we'd write the conditional probability with this vertical line. The probability of E, and the vertical line is read as given that. So that's the probability of E given F. So that new notation, the vertical line is read given. So this is the probability of E given F, or given that F has occurred. Probability of E given F. That's conditional probability. This is important, so take a minute to just soak it in. The probability of E given F is the conditional probability of event E given that F has occurred. That F is the additional information that we now know that we didn't know before. The vertical line is read given or given that, depending on exactly how you want to phrase it. For our particular problem, this would be the probability that the sum is 5 given that the sum is odd. Think about that a minute, because you need to understand what the probability is saying or asking before you can get an answer. And if I don't make any other point in this lecture, I want to say this and make this point. Oftentimes, if you understand how the given that condition restricts the sample space, the original sample space, you can solve this conditional probability problem without even formally using formulas. But if you really understand how the given that condition restricts the original sample space, quite often you don't really even need formulas. For example, if I told you that 2 cards are drawn without replacement from an ordinary deck of cards and asked you the probability that the second card is a heart given that the first card was a heart, they're asking me for the probability the second card is a heart given that the first was a heart. Well, if I know that the first was a heart, I'm given that the first card was a heart, then that reduces my sample space. If I know the first card was a heart, when I draw again, instead of having 52 cards in the deck, I'll only have 51 cards in the deck. And since the first card was a heart and there are 13 hearts in the deck, if the first card really was a heart, after I draw a heart out, I only have 12 left. So knowing that the first card was a heart, if I didn't put the card back and it says drawing without replacement, when I draw again, or just before I draw again, I'll be drawing from a 51 card deck that only has 12 hearts. So now the probability of that second card being a heart is simply 12 out of 51. Knowing that the first card was a heart and that it wasn't replaced reduced the sample space down to 51 cards, 12 of them being hearts, and that probability would be 12 out of 51. Simple if you know how to think about it. And if you want to reduce that to 4/17, you can. How about this one? A container has 35 green marbles, 20 blue, and 4 red marbles. 2 marbles are randomly selected without replacement. If E is the event that a green marble is selected first and F is the event that the second marble is not green, compute the probability of F given E. I will say that when I see these problems where the events are given letter names, if they tell me what the actual events are, my inclination is to go ahead and replace the letters with an actual phrase representing the event. So if F is the event that the second is not green, I'll just write that out. And if E is the probability that the first was green, I will just write that out. It's up to you, but I think it's easier if you do it that way. Now, having done that, remember, we're given that the first draw resulted in a green marble, and we're doing it without replacement. So if there started off being 59 marbles, after the first draw there are only 58 marbles, and the one that was drawn was a green. So instead of 35, there are 34 green. We want to calculate the probability that the second was not green, given that the first was green. You can see that I've already put the answer up there as being 24 over 58, and I think you can see that where that came from. The denominator is simply the count of how many marbles were left, and the numerator are the number of things that are not green, a number of marbles not green, and you can see that there are 20 blue and 4 red, and 20 plus 4 is 24. So there were 24 non-greens to choose from. So the probability is 24 over 58, non-greens over total marbles left. And it's 58 instead of 59 because you were drawing without replacement. If you want to reduce that, you can reduce it to 12/29, but WebAssign really doesn't care. How about this one? 2 dice a row. What is the probability that the sum of the dice is 6 given that the row was a double? Again, you want your sample space in a table 2 by 2, 6 possibilities for the first row, 6 possibilities for the second row. You're given that the row was a double. So we want the sum to be 6 with the additional information that we rolled a double. So the probability that the sum is 6 given that the row was a double. Well, if we know the row is a double, we know that's already occurred, we can get rid of everything but the doubles. Well, the doubles are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So all of a sudden that 36 member sample space reduced down to 6 because we know that it was a double. So we'll be dividing by 6. Out of those remaining 6 choices, only one has a sum of 6, and that's 3, 3. 3 plus 3 is 6, so the probability is 1 out of 6, or 1/6. See how this works? If you can think it through, you don't really have to memorize the definitions. You just have to understand what the condition does to the sample space. How about this one? Mrs. Fraga's class has 109 students classified by year and gender. It's listed in the table below. She randomly chooses one student to collect homework. What's the probability of selecting a female given that she chooses randomly from only the sophomores? So the given that part is that she's only choosing from the sophomores. That means you can eliminate all the freshmen, all the juniors, all the seniors. So your sample space has reduced down to just the 21 sophomores. So now what's the probability of selecting a female? Well, look within the remaining choices, those 21 remaining choices, 5 of them are female out of the 21 sophomores. Notice again, I said it, but I'll actually write it. There are 21 sophomores. So the probability that the student was female, given that the person was a sophomore, is going to be the number of females over the remaining things in the sample space, which are just 21 sophomores. So your answer is 5/21. Very simple if you understand what you're trying to do. This might be a good place to mention that we can use the conditional probability ideas to modify the product rule for independent events that we've talked about earlier to handle cases where the events are dependent, as we've been talking about. Recall that the product rule for independent events says if 2 events, E and F, are independent, then the probability of E and F is equal to the probability of E times the probability of F. But if the 2 events are dependent, we can modify that slightly to say that the probability of E and F is equal to the probability of E times the probability of F given E. It's still a product, but you're using that conditional probability. If 2 events, E and F, are dependent, then the probability of E and F is the probability of E times the probability of F given E. Let's do an example. Let's draw 2 cards from a standard deck of 52 without replacement. What's the probability that your first card is a spade and your second card is red? Recall your deck of cards. You have to know enough about a deck of cards to answer these sort of questions. The first card being a spade causes you to look at the deck of cards and realize that there are 13 spades in the deck. The second card being red causes you to look at the deck of cards and realize that 26 of those 52 cards are red. The product rule for dependent events says if 2 events E and F are dependent, then the probability of E and F is the probability of E times the probability of F given E. Here, that would be the probability of the first being a spade and the second being a red is equal to the probability that the first is a spade times the probability that the second is red, given that the first is a spade. And that should be easy enough to figure out. What is the probability that the first is a spade? Well, as we said, there are 13 spades in the deck, so the probability of drawing a spade on that first card is 13 50-seconds. Also, keep in mind, you could reduce 13 50-seconds to 1/4 if you want to. Don't necessarily have to, but you can. What about the probability of the second one being red, given that the first one's a spade? This is a little tricky if you don't think, because you're drawing without replacement, which means if you draw out a spade, you're not putting it back in. So the deck now only has 12 spades and 1 less card, so that would be, instead of 52 cards in the deck, there would only be 51 in the deck. There are still 26 red cards, but now one of the cards has been taken out and not replaced, so there are only 51 cards left in the deck. So the probability of getting a second red, given that you've taken out a spade, is not 26 out of 52, but instead is 26 out of 51. And if you multiply 1 times 26 and 4 times 51, you'll get 26 over 204. And as I said, you could have left that 1/4 as 13 50-seconds. You did not have to simplify it, but it's nicer if you notice those sorts of things, I believe. So the answer will be 13 over 102 if you simplify it as much as you can. WebAssign doesn't really care if you simplify fractions, but if you want to, you can. How about this one? 3 cards are dealt from a well-shuffled standard deck of 52. What is the probability that the first card is red, the second card is black, and the third is red? And give your answer as a fraction. Remember, 52 cards in the deck. The deck of cards has hearts, diamonds, spades, and clubs. There are 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, and 10s, and then there's the jacks, queens, kings, which are the face card, and then there are aces. 52 cards. The product rule says that the probability that the first one's red and the second one's black and the third one's red is the probability that the first one's red times the probability the second one's black, given that the first one was red, and times the probability that the third one is red, given that the first 2 choices were made. So those last 2 are conditional probabilities. It's basically the probability of getting a red, the probability of getting a black, the probability of getting another red, but you're taking into consideration what's already been drawn out, because if you're dealing cards, they're not being put back in, so they're not going back in, so that means it's without replacement. That's what makes it a conditional probability. So anyway, we want to find out what is the probability of drawing that first card red. Well, there are 26 cards in the deck of 52, so that's 26 over 52. That also happens to be 1/2, so if you wanted to write it as 1/2, that's perfectly okay. I'll leave it that way for the time being. But what about drawing the second black? Now you've got to be careful. After that first card is dealt, it doesn't go back in, so there are only 51 cards left in the deck. I drew out a red, so there are only 25 reds and 26 blacks. So the probability of getting a second black from that deck of 51 cards is 26 out of 51. I want a black, and there are still 26 blacks in there, but there are only 51 cards in the deck. So the probability of getting the second black, given that the first one is red, is 26 out of 51. And finally, what is the probability that the third one is red, given that the other 2 were chosen? Well, now you've taken 2 cards out of the deck, so there are only 50 cards, and you've taken 1 of each color, 1 red, 1 black, so there are only 25 reds and 25 blacks left in the deck, so the probability that the next one is red is 25 out of 50. And according to the product rule, all you've got to do is multiply those together. giving your answer as a fraction, if you just multiply straight across, you'll get 16,900 divided by 132,600. Now you can simplify that any way you want to. In fact, you could have gone back up to the top and simplified 26 out of 52 as being a half and 25 out of 50 being a half, and you could have gotten a lot nicer answer. But as I said, WebAssign really doesn't care. But if you did want to simplify it, you could get it all the way down to 13 over 102. I want to wrap up this section by going back to 3 problems that I covered in section 12.4, and at the time I said that I would show you what I consider to be an easier way to solve those 3 problems. So let's do that. If you look in the upper right hand corner of the screen, you'll see I brought up a screen capture of that problem that I'm talking about, at least the first one of those, and how we solved it before. That problem said if we roll a standard die 3 times, what is the probability we get at least 1 4? Instead of solving it the way I did in section 4, I want to solve it using the complement rule, which we did use in section 4, combined with the product rule for probability that we covered in this section. I think you'll find this much easier. To do that, I start off with the complement rule just as before. In this case, the probability of getting at least 1 4 is 1 minus the probability of not getting any 4s, or getting 0 4s. Now, the probability of getting 0 4s is the key to this whole calculation, because once we get that, we just say 1 minus that and we'll have the answer we're looking for. But the probability of getting no 4s, according to the product rule of probability, is simply the probability of getting no 4s on row 1 times the probability of getting no 4 on row 2 times the probability of getting no 4 on row 3. That's what we learned in this section. But each of those probabilities is easy to calculate, because if you don't want to get a 4, you just have to get anything but a 4. And also, because you're rolling die, the rolls are independent, so the probabilities don't change. So those will be 3 probabilities that are exactly identical multiplied together. Well, what is the probability of not getting a 4 on row 1? Think about it. If you're not going to get a 4 on row 1, you can get either a 1, 2, 3, 5, or 6. That's 5 possibilities out of 6 possibilities. So the probability of that happening is 5, 6. And because the rows are independent, it's going to be 5, 6 on the second row and on the third row. So the probability of getting no 4s on any of those 3 rows is simply 5, 6 times 5, 6 times 5, 6, which is 125 over 216. Remember, we want to know the probability of getting at least 1 4, so we have to take that and subtract it from 1. So you have 1 minus 125 over 216, which leaves 91 out of 216 as your final answer. And if you look up in the corner of the screen on the right, you'll see that's exactly the answer we got before. I think this solution is much easier. Let's do another one. Up in the upper right-hand corner, I put up the solution that we used to solve this problem in 12.4, and you can see the answer in the solution technique. I'm going to do the same thing with this problem. This time we're drawing cards. We're drawing 3 cards from a standard deck without replacement, and we want to know the probability of getting at least 1 that's a face card. We'll start off just as before using the complement rule, but I want to do the rest of the problem using the product rule for probability that we learned in this section. So the complement rule here says the probability of getting at least 1 face card is 1 minus the probability that we don't get any face cards. But remember, we're drawing 3 times and we're drawing without replacement, so keep that in the back of your mind. The probability of getting 0 face cards on 3 draws by the product rule is the probability we don't get a face card on the first draw times the probability we don't get a face card on the second draw times the probability we don't get a face card on the third draw. But because these draws are without replacement, these are conditional probabilities, and they're going to change between draws because you're not putting the card back in. So keep that in mind. What is the probability of not getting a face card on the first card? Well, if you look back in the upper right-hand corner, you'll see that we talked about this. There are 52 cards in the deck. There are 12 face cards. There are 40 cards that are not face cards. So the probability of not getting a face card on the first draw is simply 40 out of 52. But when we go to calculate the second probability, the probability we don't get a face card on the second draw, this is a conditional probability because we're not putting the card back in. So we got a non-face card on the first draw, so that leaves only 39 of them out of 51 because we're not putting the card back in. So the probability on the second draw of not getting a face card, well, there were only 39 face cards left out of 51 cards. And then you can see the pattern. By the time you get to the third face card, you're down to 38 face cards in the deck with only 50 cards in it. So the probability of getting no face cards by the product rule is simply the product of 40 52nds times 39 51st times 38 50ths, which comes out to be 59,280 over 132,600. Now this particular problem asks us to calculate and leave the answer as a percent rounded to one decimal place. So we're going to have to change this to a decimal. So this is probably a good time to do it. You really have the probability of getting at least one face card being 1 minus the probability that you don't get any face cards, and we just calculated that to be 59,280 over 132,600. Probably a good time to change that fraction to a decimal. We're going to change the answer to a percent, and then we're going to round it. So carry plenty of decimal places, and then when you round later, you will be accurate to one decimal place as a percent. So carry plenty of decimal places, and I carried it to 5. So when I divided 59,280 by 132,600, I got 0.44706 to 5 decimal places. 1 minus that is about 0.55294. But remember, the problem said to change it to a percent and then round it to one decimal place. Changing to a percent involves moving the decimal place 2 places to the right, so that would become 55.294%. And now we want to round it to one decimal place, so the 0.2 becomes 0.3. And if you'll look up into the upper right-hand corner, you'll see it's exactly the answer we got before, and I would contend that this solution is much easier. Let's do one more. From the earlier section, we did a problem about rolling a pair of dice 3 times and finding the probability that we get a sum of 6 at least once. And again, we're going to round our answer to 3 decimal places here. We'll start off with the complement rule just as before back in the previous section, but again, I want to use the product rule for probability to solve this problem instead of the section 4 technique. So according to the complement rule, the probability of getting at least one sum of 6 is 1 minus the probability of getting no sums of 6. So the key to this whole problem is finding the probability of getting no sums of 6. According to the product rule, that will just be the probability of not getting a sum of 6 on the first row, not getting a sum of 6 on the second row, and not getting a sum of 6 on the third row. Remember, we're rolling 2 dice. And you've got to remember, when you're rolling 2 dice, you go back to your sample space. There are 36 possibilities, and we've been putting that in a table. So 36 possibilities, and if you don't want a sum of 6, you can see where I've circled all the sums that are not 6, and the only ones that aren't circled are 5, 1, 4, 2, 3, 3, 2, 4, and 1, 5. That's 5. With the 36 together, that means there are 31 that are not sums of 6s over a possible 36 sums, irregardless of whether it's a 6 or not. So the probability of getting no sum of 6 is 31 over 36. And as in the problem before last, these rolls are independent. Rolling something on a first roll of those 2 dice has no effect on the sum you get when you roll again. Those are independent events, so the probabilities don't change. So it's going to be 31 over 36 times another 31 over 36 times a third 31 over 36. And if you multiply that out, you'll get 29,791 over 46,656. So the probability of getting at least one sum of 6 is 1 minus that fraction. Again, they're asking us to leave the answer as a decimal rounded to 3 decimal places. So we want to change that to a decimal. And carry plenty of decimal places so you don't get a rounding error. That comes out to be about 1 minus 0.63852, and that's about 0.36148. Into 3 decimal places, that would be 0.361. If you look back in the upper right-hand corner, that's exactly what we got the other way. And again, my contention is the 12-5 technique for these problems is much easier than the 12-4 technique.